All right, so today what we're going to do is look at how line integrals and work are related and how we can seamlessly go back and forth. Now, we talked about if I have a force function, that's kind of obvious. If I do a force function dotted with a distance, I'm going to get work. But since the force is variable and paths typically are variable, it's not a simple matter of just taking a couple of simple vectors and doing a dot product. In fact, integration's generally involved. So let's consider the following, that I've got a force, and it's of the form MNP. I'm going to do this in 3 dimensions, but the analogies in 2 still work. And let's say we have a path R of t. Okay, R of t is my path. Now, I can't dot force with the path. That won't work because at any particular place, right, it's the direction that has everything to do with it. Remember, force it's how much force in a particular direction, and on a path, the direction is always the tangent line, which means the direction is always the derivative. So therefore, I need to do the force, and I need to dot it with the derivative. Now, the problem is, this is not work. This would be work per time because, again, this is distance per time, this is force. So if I do this, but I integrate, and again, I would integrate in this case with respect to t, this would be work. All right. Now, why can't I just do the dot product of this? Well, I could if this was a line, but this is not a line. Okay. So as I'm moving in different directions, right, my force along a path is going to be different at every point on the path. So this is sort of the starting point. So now let's go and say, well, what exactly is dr dt? So let's look at all the pieces of this puzzle here. Dr dt, of course, would be dx dt, dy dt, dz dt. Therefore, f dotted with dr dt would be m dx dt plus n dy dt plus p dz dt. And now I would take this result and I would integrate it with respect to t. So if I write f dotted with dr dt integrated with respect to t, usually this is simply abbreviated f dot dr. For the same reason, when you do a u substitution and you replace, u as some function of x and then du dx, you always write du as chain rule factor x. So in the integration, I'm integrating with respect to dt, it's going to end up looking like this. But what is this looking like? This will be m dx dt plus n dy dt. I'm going to have to write a little smaller here, plus p dz dt, all integrated with respect to t, and using the same reasoning, dx dt integrated with respect to t is the integration with respect to x. So this would become simply m dx plus n dy plus p dz, which should look familiar. That's kind of what we did last day. We looked at integrals of this form, and I said, oh, they're just work. Last day, I think we just did the first 2. We just did 2-dimensional stuff. So right now, we have multiple representations for work. Probably the most universally common is this one, which technically is really dr dt integrated with respect to t. But I also will ask the integral in this question, in this form. So when it's in this form, now going backwards, m, n, and p came from the force vector. When I did the force dotted with the speed, or I should say the velocity integrated with respect to time, that simplified to this. Now there's one other version that we also might see, and that's if we integrate along the curve using arc length as the parameter. We talked about that one last day. So let me put that one here. These are all the different representations of the exact same thing. So another representation might be this. I know what T of T is, but remember T of S is defined to be the derivative of R evaluated at S, or I should say with respect to S. Okay, this goes way back to the beginning of the course. So if I'm doing my tangent vector, but my unit is not time, but actually increments of the arc length, okay, we know those two statements are correct. But then this would become dx ds, dy ds, dz ds. These are small s's. So somebody asked last day, what's the difference? Big S we generally use for surface area parameter. Little s we use for the arc length. I know it's a terrible choice. So you want to make sure that they look, in fact, quite different when you're doing them. So now what if I do f dotted with t of s? Well, then that gives us m dx ds. This is going to look very familiar, but it's actually not the same thing because the derivative with respect to s is not the same as the derivative with respect to time. So now when I do this and I integrate, I'm going to integrate with respect to s. So we write it this way, f dot t ds. I'm integrating with respect to s. That would be m dx ds plus n dy ds plus p dz ds. Can you mute yourself, please?
Hago todo lo que puedo hacer, no vale nada, nada vale.
Let's wait. Mute yourself. All right, so we get this, but then the same reasoning. If I'm integrating with respect to s, this just becomes m dx plus n dy plus p dz. And the beauty is it didn't matter if I was integrating with respect to time or with respect to arc length, I still got the same form of the integral. So these are the different representations of work. And so let's do a couple of examples before we move on to the next bigger stuff. So the question, let's do a really simple one. Let's suppose that, let's say, I want to make this not too complicated. Let's say f, and I'll do it in 2 dimensions for now. And let's say that this is, I'll use trig-ish stuff, 4xy and 2y cubed, r of t, let's just say, let's keep it really simple. Let's say I'm moving along a circle. So r of t would be, let's say, cos t sine t. So basically I'm moving around a circle and this is the force at every point. What we'd like to find is, what is the work done here? So in order to find the work done, I'm going to do f dot dr dt. Fairly simple notion. So what is dr dt? Dr dt would be what? In this case here, dr dt would be negative sine t cos t. Now I want to do f dotted with dr dt. I can't do a dot product of x's and y's with t's. That won't work. Does anybody have a suggestion? I'm going to do f dotted with this. That's my path, which basically means I'm saying x equals cos t and y equals sine t, right? X of t, y of t. Anybody got an idea how I can make this work? It's actually quite simple. Right, this is what we did last day. This is my parameterization of my path, right? I have x and y now in terms of t. So then I just simply replace that x and y with these guys. So my force as a function of t will be, all right, so 4 times x times y. So that will be 4 cos t sine t. And then 2y cubed would be 2 sine cubed t. Okay, now the process is not so bad. I don't know if my integral is going to be easy, but I know I can clearly state my integral. I know that won't be very hard to do. So now f dotted with dr dt will simply be the dot product of these two things. So this would be what? negative 4 cos t sine squared t. This would be plus 2 sine cubed t cos t. Okay, so now the integral, I'm actually just going to say it, work equals the integral of f dot dr. That's sort of the generic way of saying it, over the path c. Now, what I didn't mention was, what was our path? We're moving on a circle, and let's say we're doing one complete loop of the circle. How's that? Let's say we're going from, actually, no, let's not do one complete loop of the circle. Let's say we're going from, let's say just the first quadrant of the circle. How's that? Whoops, 0 is less than t is less than pi over 2. I should have had that in there at the beginning. So that's our path. So when I do this, those will be my t limits. So now what I've got is I'm integrating this over these limits here. So negative 4 cos t sine squared t plus 2 sine cubed t cos t, all integrated with respect to t. Well, this makes it really simple, because if my u is t, then my du is cos t, and each one of these is going to be the form u to a power du. So that's kind of nice. So the first one, u squared du, so I'm going to have a 1/3 u cubed, so that'll be negative 4/3 sine cubed. Here I have u cubed du, so it'll be 1/4 u to the 4th times 2, that'll be 1/2 sine to the 4th, integrated. Well, I know that sine of pi over 2 is 1. I know that sine of 0 is 0, so my final answer is just going to be negative 4/3 plus 1/2. So what will that be? It'll be negative 8/6 plus 3/6, or negative 5/6. Okay, any questions? This is just very mechanical, and the integration itself should be relatively simple. Okay, there's just nothing about the problem that's complicated. So here's the thing. The most common way a question is asked is you're given a force, you're given a path, you're asked for work. You're going to do f dot dr dt, but you have to rewrite f in terms of your parameterization, because you can't do a dot product with x, y, and t all at the same time. That won't get you anywhere. So I'm going to convert everything to a function of t in order to do the integration. Now, we're just hoping that this integral is not too terrible, right? We're just hoping that it's fairly simple. So
But what was your u?
in my u would be sine t, because then my cos t would be my du. So if my u is sine, then this is u squared du, this is u cubed du, makes the integral much simpler. If I use a more complicated thing, I rarely will change a variable when it's that simple, because then you got to rewrite the whole thing with the change of limits and, extra work for what should be a relatively simple integration. Now I'm going to do a series of problems so we can get to a certain point. And the series of problems we're going to do, I actually wrote them down so I can read them. We're going to do the following. We want to evaluate 6xy dx plus 3x squared minus 3y squared dy over the path c. But I'm going to give you 3 different paths. Okay, we're going to say from 0, 0 to 2, 4. Fit that in there. But we're going to do 3 separate paths. The first path, called C1, is going to be along the line y equal 2x. Quick check, right? 0, 0, 2, 4. Okay. My second path is going to be along the parabola y equals x squared. And my third path is going to be along the cubic. So I have 3 completely different problems here, and I'll illustrate it here. So I'm going from 0, 0 to 2, 4. actually, I'm not gonna be able to fit that. Sorry. That's my C2. And then the cubic will be a little bit flatter. Come up here. There. I'm going to integrate. So my work that I compute, I'm going to compute 3 different ways here. So we have 3 different problems, 3 different integrations, but each one only has one path. So I'm not going to have to add multiple integrals. Last day we did a problem where we had multiple integrations and we had to add each one. I'm going to keep it a little bit simpler. But I wanted 3 different paths, all beginning and ending at the same place, just to kind of see what's going on here. And we want to calculate the work done on this path, this path, this path. So if I asked you, what is the force, this is m dx n dy. So my force vector automatically is this. This is not hard. This is the direct translation. That's m, that's n. So this is of the form m dx plus n dy. So the force vector is this. Now, what is my r of t, if you will? Well, my r of t would be in here, but I'd need to parameterize each of these independently. So I don't need to actually set up r of t so much as do the correct parameterization and then go back to the original problem. So let's do each one at a time. So let's start with C1. On C1, what would be more efficient for x to be, for t to be x or for t to be y? It doesn't matter. But which one's probably less work? Unless you're using y equals x, it is always easier in one direction than the other. Every problem that can possibly exist, unless y equals x, one will always be easier than the other. Anybody want to suggest, should I let my t be x or y?
Wait, why?
If I make my t be y, then what is x?
Yeah, that's a good point.
Usually, here's the hint. If one variable is isolated, without exception, you always pick the other variable because then there's no algebra. That's the first suggestion. Secondly is avoid fractions and roots at all costs. If I let t be x, then y is 2t. If I let t be y, that's correct, but then x is half t. And I actually have to think about it and solve it. That's what I'm saying. One direction is going to be easier because I don't have to think about it. I can't get a different answer, by the way. So I'm going to let x equal t, and then y is automatically 2 times. This is a simple rule of parameterization that hopefully you learned even in baby algebra. When you're writing y as function of x, always pick x to be the parameter. And then y is just a function of that parameter. And you don't have to work backwards and solve. So now dx is 1 dt, dy is 2 dt. And what will the range of values of t be? I'm going from 0, 0 to 2, 4. So t will range from what to what? There's no calculation going on. This should be automatic. There's not even a thought process. It's not like I have a lot of choices. It's either 0 to 2 or 0 to 4. Which is it?
0 to 2.
And how come?
Because it's x.
Because x was t. So you're looking at x's interval. That's it. If you'd picked y to be the t, then you'd go 0 to 4. And that, by the way, that's important because that's another area where we sometimes make a mistake. We did the correct parameterization, but we looked at the wrong variable to choose our interval. And that will obviously affect our final answer. So if I do this correctly, now when I go back to here, I'm going to replace x with t, I'm going to replace y with 2t in both statements. Okay, and that's huge. So my integral now is going to be 6t 2t dx is 1 dt plus 3t squared minus 3 times 2t squared times 2 dt. So you notice how I put the dt on the outside. Yes, you could write dt, then you got to rewrite it again with the dt. I'm too lazy to do that. And you don't integrate with 2 dt's in there. You only integrate with 1. Now, let's clean this up if we can. All right, so I'm looking at this going, I think every term is going to end up with a t squared. Here I'm going to have a 12t squared. That's going to be 2 squared 4. So that's 3t squared minus 12t squared, which is negative 9t squared, but it's also times 2. Aha. So I've got 12t squared minus 18t squared. Does everyone see that? 12t squared minus 18t squared. That's negative 6t squared, I believe. Okay. Now, what about my limits of integration? We already said they're going to be 0 to 2. Well, that's not so bad. I think I did this right. Hopefully we didn't make any algebra boo-boos. Again, 6xy dx, 3x squared minus 3y squared dy. Okay, so this is going to give me negative 2t cubed from 0 to 2. So that would be negative 16. If I did this right, I got negative 16. So I'm just going to write it right here. Our first answer was negative 16. And I'm going to write it there because I'm going to need to erase all this. Because now we're going to do it again, but we're going to do it for this one. Okay. So along C2, again, what choice should I make? Y equals x squared, which would be an easier one? X equals t or y equals t?
X equals
X equal t.
X equals t because then y is t squared. If I pick y equals t, then x is square root, which is fine, but then I got to take the derivative of the square root. And I can do that. I'm a calculus guy, but that's extra work. I'm lazy. I don't want to do extra stuff if it's not going to change my answer. So I'm going to have x equal t, then y is going to be t squared. And again, what's the range of values on t? Well, if x is t, it's going to stay the same, 0 to 2. Okay, dx is 1 dt, dy is 2t dt. It's not a constant this time. Okay, so now let's write our integral. So in here, I replace everything with what I just said here. So we're going to have the integral from 0 to 2, 6t t squared times 1 dt plus 3t squared minus 3 times the square of t squared times 2t, and then all dt. Okay, I think everything looks good there. All right, let's check this out. So let's simplify. This is going to be 6t cubed. Right there, that's 3t squared minus 3t to the 4th times 2t. So now we've got 6t, not 2t, 6t cubed minus 6t to the 5th. And I'm adding it to this. So obviously this integral is completely different than the last one. It doesn't even look similar. So I have 6t cubed plus 6t cubed minus 6t to the 5th. Beautiful. All right. So let's go ahead and proceed from here. So it looks like when I integrate this, this is going to be t4, so 3t to the 4th minus t to the 6th evaluated from 0 to 2. Beautiful. All right, so that gives us 16 times 3, so 48 minus 2 to the 6th, that'd be minus 64 or negative 16. Okay, cool. Huh, that's interesting. Go figure. Got the same answer. Wow. I wonder if that's important. Maybe, I don't know. All right, now we have a completely different path. We have a completely different path for the third one. This one's going to be a little bit beefier probably on the integration. So I think we've pretty much figured out, let's let x equal t. Let's just keep going in that route. And then y would be 1/2 t cubed. So then the dx is 1 dt. The dy is 3/2 t squared dt. So going up to here, my integral from 0 to 2, which will look different than the first two, 6t 1/2 t cubed, oops, not yet, oops, times 1 dt plus 3t squared minus 3 times 1/2 t cubed squared, and then times 3/2 t squared, all dt. So this one's a little bit busier than the first couple. So here it looks like we have 3t to the 4th. Over here, this term here is 1/2 squared times -3, so that's -3/4 t to the 6th. And I'm multiplying all that by 3/2 t squared. So it looks like this quantity here is going to be 9/2 t to the 4th minus 9/8 t to the 8th. Whew, it's messy. All right. So now I've got a 3t to the 4th plus 9/2, so that'd be 6/2 plus 9/2 is 15/2. So let's do that. I've got 15/2 t to the 4th minus 9/8 t to the 8th. Beautiful. Well, hopefully this isn't too ugly. So that's going to be t to the 5th times the 5th, so that'd be 3/2. Quick check. Boom, boom, boom. This will be t to the 9th times the 9th, so it'd be minus 1/8. Quick check. Okay. So t to the 5th, that's 32. 16 times 3, so it'd be 48. 2 to the 9th, that'd be 512. But I'm dividing it by 8, so that's just 64. And we got the same thing. Huh. Now, just so you know, if I take different paths to get to the same place, you don't get the same answer in general. That doesn't happen. Infinitely many problems. If I go from point A to point B on different paths, you get different answers, period. But I used 3 different paths and I got the same answer all 3 times. Do you suppose if we chose another path, we'd get the same answer? For this problem, yes, because there was something very special about my original force. Huh. My original force came from something. I'm going to erase this. It turns out that original force, this guy right here, I'm going to erase the other stuff because we've got this down. I'm going to come back to this later. This original force is the gradient for f of xy equal to 3x squared y minus y cubed. This force is the gradient of this vector, which means, this function, which means this f is the potential function that produces this vector. Now, you didn't know that. I'm telling you that. I reverse engineered it, in other words. So what does that make this vector? What's the word I'm looking for?
Conservative.
It's conservative. And I said that's the most important kind of vector. A conservative vector, in the simplest notion, if a vector is conservative, then when you're going from point A to point B, all paths produce the same result no matter what, which is really cool. When your force vector is conservative, then we say the integrals are, the word is path independent. independent, which obviously means independent of path. I'm going to get the same answer no matter what path I chose. Every path produces the same answer. Well, if that's the case, if every path produces the same answer, should I just automatically go for the easiest path? No, it's even easier than that. If every path produces the same answer, then just take your potential function and evaluate it at the endpoint. So I'm going to show you that. You're going to like this. This is the most important thing we've done up to date. If I had taken my potential function, and the way we write is we evaluate it from 0, 0 to 2, 4. Kind of like when you write a definite integral, except I'm going from point to point as opposed to scalar to scalar. So when I evaluate this at 2, 4, 3 times 2 squared, that's 12. 12 times 4, that's 48. Minus 64. And then when I evaluate at 0, I get 0. Oh, okay. Oh, you're kidding me. You mean all of that work we did, the parameterization, the setting up the new integral, the integrating the whole thing, doing all that stuff, it was all correct. But I didn't need to do it. If I could have just figured out what the potential function is, all I would have had to do is evaluate the potential function at the start and finish. That's what it means to be path independent. It only matters where you start and where you finish, not how you got there. So if I have a conservative vector, man, that makes things so much easier. So the question is, how in the world would have I've even known this was a conservative vector? A. And secondly, if I did know it was conservative, how do I work backwards to get the potential function? B. Well, that is basically the point of the rest of today's class, because that is the most important process that we're going to do with vectors. So the first thing is, how in the world would I have known that it was conservative? How in the world would I have known that it came from something? Well, actually, that part's the easiest part. Okay, and then we're actually going to do the calculation just to show how it's done. Okay. So by the way, I'm going to change the original question now. I'm going to change the original question. And here's actually how we would write it. I want you to evaluate this integral from here to here, which is not possible unless the integral is path independent. The integral being path independent is the same as saying the force vector is conservative. The vector is conservative, the integral is path independent. This question already implies that it's path independent, because otherwise, if every path gave you a different answer and I don't tell you the path, then there's an infinite number of answers. I only want one answer. Okay, so how do I know this? Well, let's just say in general. Let's suppose we're starting with f of x, y. Now, I'm going to define my force vector to be this. We'll do the three-dimensional one next. Okay, everybody understand? That's my force vector. My force vector is now conservative. How will I know that? Because I'm going to see, in other words, I'm going to see something that looks like this. Okay, think partial derivatives. Okay, tell me about the partial of m with respect to y. What does that equal? What is the partial of m with respect to y? Wouldn't that be little f xy? All right. Similarly, what's the partial of n, that being n, with respect to x? Well, wouldn't that also be little f xy? Oh. If the partial of m with respect to y and the partial of n with respect to x are both the same thing, by the way, we started with a conservative vector, then for a two-dimensional vector, here's an absolute. If my two-dimensional vector is the gradient vector of my potential function, then we know it's conservative. That's where the term comes from. But then this will always be a true statement. The partial of m with respect to y will always equal the partial of n with respect to x. This is your test for conservative. It's actually this simple. So let's go back to here. Let me erase that for a moment. So if this is my m and this is my n, then in this problem right here, what is the partial of m with respect to y? Anybody? What is the partial of m with respect to y? Just holler it out. Nobody?
0.
No. The partial of m with respect to y? What's the derivative with respect to y there?
Six X.
How about 6x? Yeah, that's like the easiest thing we've done all semester. By the way, you can't miss that, like, ever. Yeah. What's the partial of n with respect to y? Oh, excuse me. What's the partial of n with respect to x?
6X as well.
That's also 6. I'm gonna write like this. Oh, so my test was test this guy with respect to y and this guy with respect to x. If they are equal, that means it came from a potential function. And by the way, the vast majority of time, they're not going to be equal. But in this case, they're equal. So I'm going to put a little check. So we'd say that f is conservative. And we would say the integral, these are two different statements that are saying the same thing basically, is path independent. The integral is not conservative. The integral is a numerical value that you will achieve no matter what path you take. The force is a vector that is a conservative vector. So our test for conservative is really simple. I just test the partial derivatives. Why? Because if this was conservative, then this is already this, and this guy here is already this. So I take the cross partial, and if they're the same, then there has to be a potential function. That's it. It's actually that simple. So testing a vector to see if it's conservative is never going to be a challenge. It just involves partial derivatives. Now the challenge will be, how the heck am I supposed to find f then? How am I supposed to find this f? Well, if m and n are partial derivatives, that means I'm going to find my potential function by integrating. You see, if I integrate this with respect to x, or I integrate this with respect to y, that should produce my original little f. So let's try that. So I'm going to claim that f of xy is equal to the integral of 6xy dx. Or it's the integral of 3x squared minus 3y squared dy. As an absolute mathematical statement, there is no problem in existence where you do both, ever. Because if you're lucky, you'll get the right answer in the end. But I found that every student, I've taught tens of thousands, every student who does both and tries to make it work, absolutely 100% of the time gets the wrong answer because they're trying to equate things. It's impossible to equate the results. Okay, you're going to see in a moment. You can't equate results. You just do one. Which one do you do? I always do it the same way. I do that guy. I just do the first one. You can do either one, but there's actually no advantage gained because you're still doing the same integrations. So when I do this with respect to x, what do I get? With respect to x.
6y. Oh, integration, sorry. 3x squared y.
3x squared y. Now the question is, plus what? This is the whole key to the problem. Is it plus c? Is it plus c? It might be, but it's probably not. What do you mean it's probably not? Whatever my f is, when I differentiated f with respect to x, I got this. What happens to purely y terms when I differentiate with respect to x?
They go to, oh, they gain an x?
They become, when I differentiate a purely y term with respect to x, what does it become?
Becomes 0.
Yeah, as if you were differentiating constant. So when I'm integrating, it's not a plus constant, it's plus function of y. Oh, because if I differentiate this with respect to x, that will go away. Now, that means what I have here is either purely y or it's still a constant. It can be a constant. But if I write constant and there should have been a y, maybe it was e to the y, cosine y, y to the 10th power, I won't get the right answer if I write plus c. So I write this. Now what do I do? Well, if I said, what's the partial of this with respect to x, I get this. If I say, what's the partial of this with respect to y, I get this. So that's my next step. What is the partial of f with respect to y? Let's differentiate this with respect to y. And what would I get? With respect to y, I would get what there?
3x squared.
3x squared. And when I differentiate g of y with respect to y, I simply get g prime of y. And by the way, that's not a partial derivative because g is only a function of y. Okay, now what do I do with this quantity? I now equate it to this quantity. Now I'm almost done. Oh, 3x squared plus this equals, okay, I'm pretty sure now I know that g prime of y must equal that. Everybody got that? My g prime of y is a function of y. That makes perfect sense. So now what's g of y? Well, that'd be the integral dy, which is easy enough. That's just going to be negative y cubed. There's no other variables. So I'll go ahead and put plus c now. Now I can say with certainty, f of xy is 3x squared y minus y cubed. Now, this is, right, because we always allow for every conceivable plus constant, every antiderivative. When you evaluate a definite integral, what happens to the plus c? And by the way, most people don't know this in calculus. Do we just ignore it?
It goes to la la land.
That's kind of how we treat it. But if every time you did an indefinite integral, you had to put the plus c, otherwise the answer is not correct. And especially if you were given initial conditions and you forgot the plus c, then you never get the right answer. You always have the plus c in an indefinite integral, an antiderivative. So why do we choose to ignore it? Well, actually, I show this when I do fundamental theorem of calculus, which I just did last week in 150. There are two places that you're going to discover. One's in Math 150, the other's in differential equations, where you actually get to choose. You get to choose the plus constant. And I'm going to show it. I'll do a really, really simple example. This is actually part of the fundamental theorem. I'm going to erase this. And because it's good, you need to know this. Otherwise, you do things arbitrarily and say, well, I'm doing this. I got the right answer, but I don't know why I'm doing this. I need you to know the why. So in Calc 1, you're doing something like this. We'll keep it simple. 3x squared dx, and we say the answer is x cubed plus c. Now I want 3x squared dx, and I want to go maybe from, 1 to 2. So I write x cubed plus c from 1 to 2. Well, that's kind of confusing. That's correct, by the way. That's correct. So now what do I got? I've got 8 plus c minus 1 plus c. And what does that give me as a final answer? 7. By the way, what if I chose c to be pi? Would I still get 7?
Yes.
What if I chose c to be negative 2? Would I still get 7? Yes. In fact, am I going to get 7 no matter the value of c? Am I going to get this answer no matter what the value of c is? Yeah. I'm going to get the same answer regardless of the value of c. There's one place in differential equations where this comes up, and this comes up at Calc 1. Since a definite integral produces the same answer no matter what value of c, and that's for every real number c, I still get the same final numerical answer, then this is one of those times you actually can choose the value of c in your definite integral. In an indefinite integral, you don't get to choose this c. You leave it as a plus c, and the only way you ever find this is if you were actually given an initial condition. Like f of 1 is 5. Oh, okay, now I know what c is. So you leave the c in an indefinite integral because every c is possible. In a definite integral, if you left the c, it would always cancel, meaning a definite integral will give you the same numerical value no matter what the value of c is. So you could just arbitrarily choose a value of c and you're still going to get the same answer. So what you choose is for c to equal 0. That's why when you do a definite integral, you don't include the plus c, because you chose it to be 0. It would never be wrong to put this in your definite integral. Just make sure you cancel it. That's all. Okay, so going back to my original problem now. This is what it looks like. I did all of the work here. So I'm going to erase this now. So I just did all of that work. So this is now technically a definite integral because I'm starting and I'm ending here. So the answer to this is 3x squared y minus y cubed. If you choose to put the plus c, it's not wrong because the plus c's are going to cancel. So I'm going to choose my c to be 0. You don't actually have to state it. Just don't write it. And as we saw earlier, that's this equals this equals this. And I think we agree this is probably easier than doing the parameterization and then doing that integration. The hard thing is finding this, but actually none of the steps I did were difficult. So this process is not that bad. So the first thing I do is I determine if my force vector is actually conservative or not. If my force vector is conservative, then the path doesn't matter, only where I began and end. So, new problem. I've got 4x squared cos y dx minus e to the x sine y dy. Is this path independent? See, as an integral, the answer is it path independent. The way you test it is you test the vector to see if it's conservative. So the first thing I need to do is say, well, what's my vector going to be? Well, what's my m in this case? M in this case is 4x squared cos y. What's my n?
Minus EX sine
Good.
Y.
Good. By the way, that's a common error that people just sort of, that might matter. Okay. So now, what is my? My is what? Partial of n with respect to y.
Negative 4x squared sine y.
I see a negative sine y. That's good. Now, what's my nx? What's nx? Partial of n with respect to x. Negative e to the x sine y? Well, they both had a negative sine y, but I'm pretty sure those aren't equal. So, when you're doing things online, it gives you the check. Now it's going to either, it's going to give you one of those. So what's my conclusion? Not path independent. Why is it not path independent? Because your conclusion here could be the force vector is not conservative. All this means is any work problem I get from point A to point B, I just have to parameterize it along that path. That's the vast majority of all problems that exist. Conservative is special. That's why we like it so much, because it makes my life so much easier if my vector is conservative. Okay. Now, this is really, really important. I'm going to give you a new notation today. What is that? It's a bullseye on an integral. When you see this symbol, which you will see basically a lot coming up, what this symbol means is I have a closed path. Okay. Now, think of it this way. I'm on the XY plane, and you started here and you end up here, and then maybe you came back to here. Okay. But in reality, if I said, how much work did I get done on the path? So here's a good question. If I start here and end here, is that a different answer than if I start here and end here, or I start here and end here, or I start here and end here? Actually, it doesn't matter where you start. All that matters is you start and end in the same place. On a closed path, there really isn't a starting and ending. It's kind of like if I'm looking at a circle and I wanted to measure, let's say, the circumference of the circle. Isn't the circumference going to be the same no matter where on the circle I start? I want to measure the area of the floor in my room, or similar. I want to measure the perimeter. Okay, so you think of a classroom. Doesn't matter what point you start, measure all the way around and finish at the same point. So whether you started in a corner or just a random spot in the room, I'm going to get the same perimeter as long as I end where I started. So this means that you have a closed loop. I still need to know what what the equations are of my path, but the closed loop means it doesn't matter where I choose to start because I'm going to end there. Now, usually you'd pick a convenient place. So this symbol means closed loop. That's it. So now here's the question. And this is our favorite question the rest of the way. I'm telling you your favorites ahead of time. Kind of like you go into a restaurant, I'll tell you, this is what you want to order. I've got mdx plus ndy, and I'm going to tell you that my equals nx. I'm not going to tell you what m and n are. I'm just going to tell you they're equal. Oh, heck, it could be this problem right here. In fact, let's make it easier. Let's say it actually is this problem right here. I'm going to put that in here. Can anybody tell me what the answer is? We're going to take that one right there. Go ahead, you can guess if you want. I have a closed loop of a conservative function, which means the integral is path independent. Well, the value of the integral is what I want. So I want a number. Well,
0.
This one was -16. This is going to be 0. Why? That's the most important part. Why is it 0? If it's path independent, then it only matters where you begin and where you end. If it's a closed loop, don't you begin and end at the exact same place? That would be the equivalent of me putting the same points in here. Oh, if I put the same points, then won't I get 0 because I'm just subtracting the same value? Yes. Path independence, if it's a closed loop, will always give you a value of 0 because you're beginning and ending at the same place, and the only thing that mattered was where you began and where you ended. So you calculate ending minus beginning, but that's going to give you the same numerical value. Both values are not 0. No. If I said start at 2,4 and end at 2,4, then I would have had -16 minus -16, which produces 0. So again, if your vector is conservative, then your integral is path independent. If your integral is over a closed loop and it's path independent, you're done. It's 0. That's why I said this is your favorite problem, because it's the one problem that doesn't require any extra work. All I had to do was this. I had to test it. You love that problem because it's so easy, so much less work. Now, I said conservative is not the norm. That's special. So the rest of the time, no, I'd have to do the calculations. The vast majority of the time, you've got to actually do the calculation like we did at the beginning. So what happens now if my vector is in 3D? This isn't going to quite cut it. Okay. So now I've got mdx plus ndy plus pdz. So I've got a 3-dimensional problem. My force vector is m, n, p. Okay. And let's not worry about what the path is. I'd like to know, how do I determine if this is conservative? Well, I actually showed you that last day. Does anyone remember? Vector in R3. What was the test for conservative? What? A major part of last day's lecture, and it's part of the next quiz.
Is it?
So if I have curly hair, that might make it easier to think about. Okay, that was terrible.
What was the curl, the 0 vector?
If the curl of f is the 0 vector, that's it. That's the test for conservative if you have a vector in R3. And I showed that last day, if you remember. I proved that. I said, let's start with a potential function f of little f of x, y, z. Then we did, okay, what's the gradient vector look like? Now let's take the curl of that specific gradient vector, and we got the 0 vector. So if you take the curl of a conservative vector, absolutely, you always get the zero vector. That's it. Piece of cake. If I take the curl of the zero vector, I'm going to get the zero vector. Yeah, that's because the zero vector is conservative. I mean, it's not very interesting, but it is conservative. So if all I have to do is take the curl, then what if I take the curl of this, the M and P, and I get the zero vector? Then we can work backwards to find the potential function in much the same way we just did it with the two variable problem. That's our next thing. That's the biggest problem we will have faced to date. Biggest, not because it's the most difficult, just the most stuff going on. So here's the question. I want to do, here's my original problem. It's let me write it. 8x cubed plus 32x cubed y dx plus 8x to the fourth minus z squared plus 6y dy plus, oh wait, it's hard to fit in, 12 x squared z squared minus 2yz minus 4z cubed dz. Now, it doesn't matter what the path is. I'm just going to put C. I've got some path. I've got from point A to point B. Now it's, you know, A, B, C to D, E, F kind of thing along a path. What I'd like to know is if this vector is conservative, is the integral path independent? Because to be quite honest, I don't want to parameterize this. This would be a nightmare. There's way too much going on here. But if it's not, if this integral is not path independent, then I don't have any other way of doing this problem. So let's start by writing down the force vector. Excuse me. So that would be 8x z cubed plus 32x cubed y. 8x fourth minus z squared plus 6y. 12x squared z squared minus 2yz minus 4z cubed. Now let's do this. So this is why I said, just to make it easier on yourself, just put these right above it. Okay. So what are we going to do? Boom, boom. So the partial with respect to y of this term here, with respect to y, that'd be 0. With respect to y, that'd be negative 2z, and that's it. Minus, okay, partial with respect to z of this. Well, that'd be 0, that'd be negative 2z, that'd be 0. Okay. Excuse me. Partial with respect to z of this, with respect to z, that's going to be 24x z squared. Now, with respect to x of this, no x is here, no x is here. So that'd be 24x z squared. With respect to x of this, that would be 32x. With respect to y, excuse me, 32x cubed, sorry. Sorry. Choking it everywhere. I really should do that more often. Now, with respect to y of this guy, 32x cubed. Do you see something good? There's much rejoicing. The vector is conservative because my curl vector was the 0 vector. Curl is not the number 0, it's the vector. My curl vector was the 0 vector. That means that this vector is conservative. It means that this integral is path independent. And because the integral is path independent, it means I now can find the potential function. So I got news for you. If one or more of these positions was not a 0, then I'm not path independent, my vector is not conservative, and no potential function exists. The number one mistake I see people make is they start integrating right away and start trying to find their potential function when they didn't check to see if the vector is conservative. And if the vector is not conservative, no matter how much work you do to find a potential function, it'll be in vain because it doesn't exist. You're never going to get an answer. Or worse, you're going to get an answer, but it's not the correct answer. So we now know the potential function exists. So our next goal is to find the potential function. We had to do this, but boy, this will make our lives easier. It's going to be some work to find the potential function, but not nearly as much work as parameterizing this and then trying to integrate it. That would be a nightmare. All right, so we're going to start by saying f of x, y, z, and that's going to equal, I'm going to take the first integral and integrate with respect to x. Okay, with respect to x, let's see if I can fit it up here. Now be careful, with respect to x, what am I going to get? The first term? Anybody?
4x squared z3.
4x squared z cubed. Now about the second term. With respect to
9x to the fourth y. Right?
what'd you
no.
get? 8 or
8x, sorry.
8, okay. That's what I thought you said. 8x to the fourth y plus. And this is tricky. Think of what we did earlier. What do you think needs to go here? I'm going to make this a little, sorry, I'm going to make this a little bit smaller because I don't.
You get a function of y and z.
Function of y and z. Beautiful. That's exactly what goes there. I'm going to make this a little bit smaller so I can fit it in easier. Sorry. Okay, so that was 4x squared z cubed plus 8x to the fourth y plus g of y comma z. Because if the remaining term or terms had y's, z's, or both, then any derivative with respect to x would have yielded a 0, as we know. But I don't write purely x, excuse me, I don't write purely y, I don't write purely z, because my next term might be y times z. So it's a function of, potentially a function of y and z. By the way, my next, it could just be a constant. There's nothing wrong with the next thing being a constant. But if I assume it's a constant and there were actually y's or z's, it's not going to work. So I err on the side of saying that's the most it can be. So now my next step is to take the partial with respect to y. I'm going to go in order. And eventually that means I'm also going to take a partial with respect to z. But it's one step at a time. You cannot combine steps here because you can only do one integration at a time. So the partial of this answer with respect to y, well, there's no y's here. How about here? With respect to y, what does that give me? 0.
8x to the fourth plus g prime. Or
not g prime, because g is a function of two variables.
G.
So either write partial of g with respect to y, or simply write g sub y. Which would you rather do?
The latter.
Yeah, this is a function of two variables, so I'm still taking a partial derivative. When I get it down to a function of one variable, in the previous example, we had I think a g prime of y. That's because g of y was the only variable. I could use prime. Prime only exists if it's a function of one variable. So if I said g prime of y, that's kind of ambiguous. It's like, well, that means g is a function of y only, because that's how that would be interpreted. So let's say the partial of g with respect to y. Now, what do I do with this? I equate this with this. Okay, so I'm going to set it equal to that stuff. Well, beautifully enough, and if I did it right, everything that does not have a y or a z in it has to cancel. And that only is this term. So this says, well, the partial of g with respect to y equals this. I'll write that down. Partial of g with respect to y equals this. Therefore, g of y comma z, which is where it came from, will be the integral of this integrated with respect to what variable? Well, this is the partial with respect to y. So I need to integrate it with respect to y. Okay. So g of yz is this stuff integrated with respect to y. If I integrate this with respect to z, then this wouldn't have been the partial with respect to y. So this will be what? With respect to y, what will this give me? Technically, that's a constant, right?
Negative y.
Y, good. Negative yz squared. With respect to y, what will that be?
3y squared.
3y squared, and then I potentially have what left over? Not a function of x. Can't be a function of x. I've dealt with the x's. Can't be a function of y. I dealt with the y's, but it still can be
Function of z.
function of z. So let's call it, how about h of z? We'll run out of letters. So everybody see there's an order here. There's a process. I'm done with x's. There's no way an x can show up. That would be impossible, because if an x could show up, then it would have shown up when I took the partials earlier. So now I'm going to restate my f of x, yz, because I have to have something that I'm taking a derivative of. Now, what is it at this point? It's this plus this. And now this is my g, so it's this plus this plus this plus this plus this. So it's all of this stuff now. 4x squared z cubed plus 8x to the fourth y minus yz squared plus 3y squared plus h of z. I'm almost there. I don't know what h of z is, but I can't imagine it's going to be very hard to find. I'm usually, when you get down to the last variable, that's the easiest step. So now what is the partial of f with respect to z? All right, well, I have a lot of z terms. I got to take into account all of them. So with respect to z, what do I get? And three terms. So what are they?
12x squared z squared
Okay,
minus 2y z, and then h prime of z on this one.
that's where I'm going to use h prime, because there's now, it wouldn't be correct notation to say the partial, because it's h is a function of one variable. There's not a partial. Now I take this, whatever the partial with respect to z is, that's what the last position is. Whatever, if I wrote up here f of x, y, z, and then this is the gradient kind of thing, this would have been the partial of f with respect to z. This was the partial of f with respect to y. This was the partial of f with respect to x, little f. That's where they came from. So now I just equate it to the last thing. There's some annoying blinking sound outside. I don't know if you guys can hear that. Now, everything that is not purely z should cancel. Oh, I am liking this right now. Now, let me tell you a problem. If I made an error anywhere along the way, errors are glaring. I have h prime of z. H has to purely be a function of z. There can't be x's or y's. It's h. So if this term here had x's or y's, or if I still have x's and y's, that's not possible, because the only thing left can be the z. So the next thing I'm going to write is h of z equals the integral of negative 4z cubed dz, which is just negative z to the fourth plus c. Now, finally, I can finish. I can be done. In this problem here, I wasn't asking you to physically integrate. So our answer to this question is just going to be the completed function. So 4x squared z cubed plus 8x to the fourth y minus yz squared plus 3y squared minus z to the fourth, and I will include the plus c because I'm not doing a definite integral right now. Wow. Now, I'm pretty sure that this is correct. I'm really darn sure. I would almost bet, except probably not a lot of money. I'm not a big fan of I'm kind of sort of almost pretty sure. How can I be absolutely certain?
Take the gradient.
Take the gradient, which should be fairly fast. And what should I get? Boom, boom, boom. That's it. That's the only check there is. This is my potential function. If I said, what's the partial with respect to X? I better get exactly that. Better get exactly that for Y, exactly that for Z. Now, in the strictest sense, didn't you test it along the way already? Yeah. But is it possible that you switched a sign or you switched an exponent? In other words, some sort of transcription error, some sort of careless error in writing the problem down. I did incredible calculus and I wrote something down wrong at the end and I have a wrong answer and it's not working and I can't figure out why. Well, if I go to check it, I might be, oh, that was supposed to be a plus sign. Oh, shoot, I got the exponents mixed up. Those are the mistakes that can easily happen. I did the calculus well, but I maybe just wrote it down badly. So the last check really is take the partial with respect to X. So that would be 8x z cubed plus 32x cubed y. Okay, great. What about the partial with respect to z? 12x squared z squared minus 2yz minus 4z cubed. That's exactly what I have here. You know, that's how long the check takes. Okay, so big picture today. We're looking at line integrals and how they exactly represent work. And in the textbooks, it usually takes about the third or fourth section before they say, okay, you've been doing work all along. We just didn't want to let you know. No, you're doing force vectors over a curve, over a distance. That can only be work. The only thing we're not doing is putting units in here. So I want you to master those problems in 2 dimensions. Because if you can master them in 2, you can do them in 3. The only difference is 3 is just more algebra, right? You have one more term. 2 dimensions is just 2/3 the work. Then we're looking at integrals and saying, is the integral path independent by testing the force vector to see if it's conservative or not? The test for a 2-dimensional force vector is very, very simple. The test for a 3 is a little more work because we had to do the curl vector. I want to remind people, I had a couple of people turn in the quizzes and the quiz you turned in today, we didn't even know what divergence and curl was. It hadn't even been defined, but I had people doing curl vectors to test their conservative. You took a gradient to find your vector. You created the vector. You don't have to test it. But I had people
I'd like to be absolutely positively sure.
No, there's nothing wrong with that. But I had people taking the curl vector of the 2-dimensional vector. And I've actually asked people, please tell me how you did that, because curl is defined to be del cross the vector. In other words, curl is only defined in 3 dimensions. There is no such thing as curl in 2. There's not even an analogy for curl in 2. So when people said, well, the curl of my 2-dimensional vector is, I'm thinking, you can't take the curl of a 2-dimensional vector. But you just check the cross partials, my versus nx. That's it. That's all you have to do. And so the check I want to be really simple, because I don't want people skipping the check. The reason people skip checks is checks can be a lot of work in some cases, but in a lot of cases, the checks are really simple. Whenever you integrated a polynomial in Calc 1, I would think you checked it immediately after. Okay, let me quickly differentiate it in my head. Okay, I integrating sines and cosines. Let me quickly check it in my head to get the signs, the plus or minuses right. That's just wise and saves trouble later. But if you're doing an entire problem like this and you don't check it somewhere, boy, that's a lot of work to have a wrong answer. So I would want you to be absolutely certain you did it correctly. So whether you go the fact that, hey, I checked it along the way and I did not miscopy. That's, by the way, that's really important. I didn't miscopy anything along the way. I'm probably okay. But if I'm filling up a whole page, maybe I'm just going to check it at the end just to be sure I didn't. You know, I think I did it once or twice. I failed to copy the exponent immediately. And then I went, oh, there's an exponent there. That's the kind of mistake that will kill you at the end. All right. That's everything for today. Next day, we do Green's theorem, which is considered one of the single most important works in all of calculus. And the derivation it's pretty huge. It takes a while. I have videos. I don't have them posted yet. I will post. Last spring and summer, I made many videos that were not Zoom lectures, just actual short videos, because those classes had to be taught completely asynchronous. That's why you guys have so many more videos than everyone else. And I have videos on that, and I don't think I have posted notes, but I have videos, and we'll do lots of examples. I need you to understand where it comes from. I don't need you to derive it. You have to understand what's going on with the fundamental theorem of calculus. You just don't have to derive it, you see. So this is a major deal, but it's also the last new information before exam 3. So Green's theorem is the last lecture. I think the next exam is 2 weeks from today. That sound about right? Yeah. with
I
one
just
more
looked at
lecture.
513, yeah, 2 weeks from today.
So what I will do, if I remember, and by the way, email reminders are really good for me. I will go ahead and post the practice test ahead of time, even though we're not done. I know people like to get a head start on that. And by the way, I'm cool with that. We have 4 weeks left in the semester. Postponing things is not a good idea this late in the semester. So if you want to get a head start on your exam prep by, starting the practice test over the weekend, by all means. I don't want to discourage you from doing that. Just understand that, there's still a little bit of ground to cover. All right, that's where we are.